A spacecraft worth $327 million vanished because two engineering teams used different units of measurement. That single sentence sounds almost too simple to be true. And yet, on September 23, 1999, NASA lost contact with the Mars Climate Orbiter forever. The spacecraft had traveled approximately 669 million kilometers across deep space over nearly 10 months. On the surface, everything appeared to be working. Beneath that appearance, an undetected error was compounding with every passing week. Then, in the final moments of orbital insertion, everything went wrong simultaneously. The orbiter approached Mars at the wrong angle, entered the atmosphere far too low, and was almost certainly destroyed. The investigation that followed would shock the aerospace community. Not because the failure was exotic or unpredictable, but because the cause was embarrassingly familiar. Two teams working on the same mission had been speaking different technical languages without realizing it. Tonight, we investigate one question the aerospace world has never fully stopped asking. How does a system as sophisticated as a NASA mission fail because of something as fundamental as units of measurement? The answer is more disturbing than you might expect. To understand how this happened, you first need to understand what the Mars Climate Orbiter was supposed to do. By the late 1990s, NASA was in the middle of a significant strategic shift. The agency had moved toward a philosophy it called faster, better, cheaper. The idea was straightforward: deliver more science missions at lower cost, with shorter development cycles. The Mars Climate Orbiter was a flagship example of this new approach. It was designed to study Martian weather, atmosphere, and climate from orbit. Scientists hoped it would help answer fundamental questions about why Mars lost its once abundant water. The mission had broad public interest and serious scientific ambition behind it. NASA partnered with Lockheed Martin Astronautics, one of the most experienced aerospace contractors in the world. The agency itself had decades of successful deep space navigation behind it. Nobody seriously questioned whether the mission would reach Mars. The real questions were scientific: what the orbiter would find once it arrived. That confidence was not arrogance. It was built on a genuine track record of extraordinary achievement, which is exactly what made the failure, when it came, so difficult to process. Inside any complex mission, there are hundreds of software interfaces passing data between systems. Most of them work perfectly. But buried deep inside the Mars Climate Orbiter mission was a quiet, undetected mismatch. Lockheed Martin's navigation software was transmitting thruster performance data in Imperial units, specifically pound-force seconds. NASA's navigation team at the Jet Propulsion Laboratory was receiving that data and treating it as metric, specifically Newton seconds. The difference between those two units is a conversion factor of approximately 4.45 to 1. That gap sounds small in isolation. Over the course of a 10-month journey across hundreds of millions of kilometers, it was catastrophic. The file responsible was the Angular Momentum Desaturation file, which recorded the small forces generated during thruster firings used to manage the spacecraft's orientation. It was this file's data that was transmitted in the wrong units throughout the entire mission. The navigational error accumulated with every thruster firing the spacecraft executed, and nobody caught it. Not because the people involved were careless, but because the system had no mechanism to flag the inconsistency. The software worked exactly as its designers intended. The problem was that two separate design intentions had never been properly reconciled. As the orbiter approached Mars in September 1999, the navigation team began noticing something unusual. Trajectory data showed the spacecraft was repeatedly off course. According to the investigation, engineers had identified anomalies in the navigational data during the final months of the cruise phase. Concerns were raised internally and submitted through JPL's navigation peer review process. But the review did not identify the unit mismatch. The verification system existed, it simply failed to catch the error. In the final days before orbital insertion, the team was operating under intense mission pressure. Orbital insertion around another planet is one of the most delicate and unforgiving maneuvers in spaceflight. The spacecraft must fire its engine at precisely the right moment, angle, and duration. Any deviation can mean the difference between capture and catastrophe. On September 23rd, the orbiter executed its insertion burn and passed behind Mars, temporarily out of radio contact. That was expected. What was not expected was the silence that followed. The spacecraft never re-emerged on the other side. Mission controllers waited. The signal did not come. After several agonizing hours, the team began to accept what the data was already telling them. The Mars Climate Orbiter was gone. Later analysis indicated the spacecraft had approached Mars at approximately 57 kilometers above the Martian surface at closest approach. The minimum safe altitude for orbital insertion was between 140 and 150 kilometers. At that altitude and velocity, aerodynamic forces would almost certainly have destroyed the spacecraft within seconds. No telemetry was received during the final approach, so the exact mode of failure could not be confirmed. A mission 10 months in the making, carrying a decade of scientific hope, had ended in silence. The investigation began almost immediately. NASA convened a formal investigation to determine exactly what had gone wrong. The Mars Climate Orbiter Mishap Investigation Board, chaired by Arthur Stephenson, began reconstructing the mission from the ground up. Investigators examined software, navigation logs, communication records, and interface documentation. They needed to trace the error back to its origin. The answer emerged relatively quickly, and that speed itself was part of what made the findings so striking. The unit mismatch between Lockheed Martin's software output and JPL's navigation system was identified as the direct technical cause. But investigators were not finished. The deeper question was not simply what the error was. It was why a system with multiple verification layers had allowed that error to survive for 10 months undetected. The uncomfortable truth was that the unit mismatch alone did not fully explain the failure. The investigation found that the interface specification, the document formally governing how data should be formatted between systems, had specified metric units throughout. Lockheed Martin's software had never been verified against that specification for the angular momentum desaturation file specifically. The assumption that metric units were being used was embedded in JPL's processes, but never formally confirmed at the interface level. Second, the concerns raised by navigation engineers during the cruise phase were not escalated with sufficient urgency through the mission structure. Anomalies were investigated at the team level, but never triggered a broader systems review. Third, the Mishap Investigation Board noted that navigation team staffing was below recommended levels. A broader review of the Mars program raised questions about whether the faster, better, cheaper approach had been applied with sufficient caution in areas requiring rigorous verification. None of these factors alone caused the failure. Together, they created a system in which a simple, detectable error could survive for months, completely undetected. The loss of the Mars Climate Orbiter represented a total program investment of approximately $327 million, covering spacecraft development, launch, and 9 months of operation. The scientific mission was lost entirely. Congressional scrutiny of NASA's management practices intensified quickly. The faster, better, cheaper philosophy, once celebrated as visionary, was now being examined as a potential liability. A separate NASA review of the broader Mars program raised concerns about whether cost reduction targets had compromised mission assurance. Within months, the Mars Polar Lander was also lost, though for different reasons, deepening the crisis of confidence around the program significantly. Reputationally, the unit mismatch became one of the most cited engineering failures in modern aerospace history. It appeared in academic courses, safety training programs, and engineering ethics curricula around the world. The embarrassment was profound, not because of negligence, but because of how preventable the failure appeared in hindsight. The Mars Climate Orbiter failure drove lasting changes in how aerospace projects manage software interfaces. NASA implemented stricter requirements for interface control documentation, ensuring that data formats, units, and conventions are formally specified and verified at every system boundary. The findings also contributed to revisions in NASA's Systems Engineering Handbook and broader mission assurance frameworks across the agency. The concept of interface verification became a prominent and non-negotiable element of mission review processes going forward. The failure also reinforced a principle the aerospace community knew in theory, but had not always applied in practice. When two teams are building the same system, every shared assumption must be explicitly documented and independently verified, never taken for granted. Investigators put it plainly in their final report: a verification system that exists but fails to catch the error it was designed to find is not a safeguard. It is a false sense of security. There is something deeply revealing about this failure that goes beyond aerospace engineering. The Mars Climate Orbiter was not brought down by exotic technology or unpredictable physics. It was brought down by an assumption, a shared belief that two teams meant the same thing when they communicated. That assumption was never written down in the right place. It was never independently checked, it was never challenged, and because it lived silently inside the system had no way to expose it before it was too late. Complex organizations face versions of this problem every day. Software teams build to different standards. Departments using the same words to mean different things. Interface assumptions that everyone believes someone else has already verified. The lesson of the Orbiter is not that engineers are fallible, that has always been known. The lesson is that systems must be deliberately designed to surface the assumptions buried silently inside them. Because the most dangerous failure is never the one you were watching for. It is always the one nobody thought to question. That is the story of the Mars Climate Orbiter. Approximately $327 million, and a decade of scientific ambition lost to a mismatch that should have been caught, in a system sophisticated enough to reach Mars, but not quite sophisticated enough to check its own assumptions. Here at Null Theory, we believe understanding how systems fail is just as important as understanding how they work. So I want to ask you something. Which system in your life do you think people trust too much today, without ever checking the assumptions underneath it? Leave your answer in the comments. And if you want to keep exploring the hidden weaknesses inside complex systems, subscribe to Null Theory. The next investigation is already waiting.